According to the legendary American professional baseball player, coach, and manager Yogi Berra, it's tough to make predictions, especially about the future. Predicting the future is the alchemy of the data world. Even though it's impossible to convert lead into gold, that didn't stop people from trying. It's the same thing with making predictions. Even though it's impossible to predict the future, that hasn't stopped people from trying. But what about using a Bayesian approach to predicting the future? Will a Bayesian approach finally crack the code? Well, let's find out. Welcome to Doco.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Time series analysis is a very large field, so this video is meant to be an introduction only. When it comes to time series analysis, the techniques used range from relatively simple models to very complex, very sophisticated models. If you feel like you're up for a challenge, the Turing.jl documentation includes a very sophisticated example of Bayesian time series analysis in their tutorials section. I provided a link to that tutorial in the description below. As for me, I'm going to cover a relatively simple example, but you'll see by the end of this video that even a relatively simple time series model is not necessarily that simple. But going through a relatively simple example will provide you with the foundation that you need to build up to more advanced models. The example that I'm going to use is inspired by a ritvikmath YouTube video titled Bayesian Time Series Talk that he uploaded in 2021. In his video, he covers a Bayesian approach to time series analysis by using PyMC, which is a Python library for Bayesian statistics. If you're interested, I provided a link to both his video and his Python code in the description below. So I watched this video and I thought to myself, great, I'll just translate his PyMC code into Turing.jl code and I'll have all the material that I need for my own Julia tutorial.
Brilliant!
Well, it turns out to be more complicated than I thought it would be, so we'll get to go on this learning journey together. Actually, a very helpful Julia resource was a 2021 Stack Overflow discussion about time series analysis using Turing.jl. I provided a link to that Stack Overflow discussion as well in the description. So what's the deal with time series analysis? Time series analysis is different than other forms of data analysis. Typically for data analysis, you have an independent variable, or set of independent variables, x. And then you'll have a dependent variable, y, whose value is determined by the values of x. On plots, the x values are placed along the x-axis, and the y values are placed along the y-axis. For time series data, there is no dependent variable y. There's only an observed variable x, whose value is changing over time. So by convention, time series plots have the time values along the x-axis, and the values for the observed variable x are placed along the y-axis. Perhaps the simplest form of time series analysis is to find a linear regression line through your entire dataset. Although linear regression is great when you're trying to understand the relationships between independent variables and dependent variables, linear regression has many limitations when it comes to time series analysis. As a result, there have been a lot of efforts to develop increasingly more sophisticated methods for time series analysis. The approach that we're going to use today is something called an autoregressive model, or AR model. Rather than drawing a straight line or curve through your entire dataset, the autoregressive approach is to take a look back at the recent past and to combine that fresh data with some random noise, whose variance is informed by history. Here's the formal definition of an AR model. X sub t is the observed data at time t. The lowercase Greek letter phi sub I is a parameter that impacts the value of x at time t minus I. The final term, lowercase Greek letter epsilon sub t, is called white noise. I know that it looks complicated in this LaTeX form, but it's basically the equation for a straight line. Now with the AR model, you can select different orders, which is denoted by the lowercase letter p. P indicates how many time steps you want to look back on your data. For today's example, we'll be using an AR2 model, which means that we'll be looking back 2 time steps. Each time step will have its own phi coefficient. So for the AR2 model, we'll be using phi sub 1 and phi sub 2. The phi parameters and the standard deviation for the epsilon value are the parameters that we'll need for our Bayesian model for time series analysis. Okay, so that's enough abstract concepts for today. Let's get to the code so you can see what I'm talking about. In the interest of time, I've prepared some code in advance. You can find a copy of my code in my GitHub repository. If you want to follow along, you can save a copy of this file in a tutorial folder on your computer. After you save the file, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square brackets. Activate the tutorial directory. Add the following packages: statsplots and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. For this tutorial, I'm going to use a random seed, so I can reproduce my data. Okay, now that we have our packages loaded, let's generate some random time series data. We're going to use the AR2 equation to generate some random data. These true values for the parameters and the length of time are from the ritvikmath video. For AR models, the absolute value for phi should be less than 1. These parameter values are the values that our Turing model will try to learn on its own. Now, it's a little tricky to generate data using the AR2 equation. Because the equation looks back 2 time steps, we need to seed our dataset with 2 initial values that we'll generate randomly using a normal distribution. Once we do that, we can use a for loop to generate the rest of the random data using the AR2 equation. The result is a vector with 52 elements, 50 elements for our actual observed data, plus 2 initial seed values. Let's set up a new vector just containing observed data. I need to pause here for a moment and point out that time series analysis is an example of a situation where it would be helpful to have zero-based indexing as opposed to one-based indexing. When using zero-based indexing, our vector of observed data would be time 0 through time 49. Time series data typically begins at time 0. But since Julia uses one-based indexing, our vector of observed data goes from time 1 through time 50. In both cases, there are 50 observations. It's just a question of where the time series begins and where it ends. Since we're using synthetic data for this example, it doesn't really matter, but just be aware of this when you're using real-world data. Okay, now that we have our observed data in a separate vector, let's visualize it. So in this plot, the x-axis shows the time steps, and the y-axis shows the values of our observed data x at any given time t. Our observed data moves randomly up and down over time, but the data hovers around 0 with a maximum value of around positive 0.25 and a minimum value around negative 0.25. Our challenge is to 1. Create a Bayesian model that fits this data, and 2. Use that Bayesian model to try to predict values going forward beyond our observed data. I'm going to type in the code for the model first, and then we'll talk about it after I'm done typing. So like with other Turing models that we've defined before, we need to define our prior beliefs and the likelihood. Phi sub 1 is the parameter for the observed value 1 time step back. Phi sub 2 is the parameter for the observed value 2 time steps back. Sigma is the standard deviation that we'll use for the likelihood distribution. The absolute value for the phi parameters should be less than 1, so we're using a normal distribution with a mean of 0 and a standard deviation of 1. The sigma value should be some positive number, which is why we're using an exponential distribution, which is always positive. For the likelihood, we're reusing the same equation for the AR2 model that we used to generate our random data. The difference here is that everything is being defined using the language of probability distributions. Like before, we need 2 initial seed elements. But rather than using values, we're using probability distributions, like everything else in a Bayesian model. And then we use a for loop to fill our vector of distributions that use the AR2 equation as the mean. Said differently, this model states that we believe that the likelihood is that the value of x at any time t is not defined by a single AR2 equation, but rather a whole collection of AR2 equations that are normally distributed. You may want to pause the video here to take a closer look at this model definition. Now that we've defined our model, the inference step is the same as we've used in previous tutorials. We're using the nut sampler again and drawing 1000 samples. In this summary statistics table, you can see the mean values for the parameters. Amazingly enough, it looks like Turing found parameter values that are pretty close to the true values that we use to generate our random data. But the standard deviation is relatively high for the phi sub 1 parameter. So this brings up the subject of Bayesian credible intervals. In Bayesian statistics, you may hear the term credible interval being used. The posterior probability represents our updated belief about the distribution of these input parameters. The so-called credible interval is the interval within which these parameter values lie. A commonly used credible interval is 95%, which means that you believe that the true value of the parameter lies somewhere within this 95% credible interval. If you look at the quantiles table below the summary statistics table, you can see a table showing various percentages for each input parameter. You can find commonly used credible intervals by using this quantiles table. So by using the extreme ends, you can find the 95% credible interval, since 97.5 minus 2.5 is 95. By using a 95% credible interval, this means that we believe that the true values for these parameters lie somewhere between the values on the leftmost column and the rightmost column. In this example, it just so happens that we know the true values for the parameters, so we can confirm that this is indeed the case. But in most real-world situations, you won't know the true values for the parameters, since the parameters are unobserved. Although it may sound similar, the Bayesian credible interval is actually very different from what frequentist statisticians refer to as the confidence interval. In frequentist statistics, a 95% confidence interval means that with a large number of repeated samples, 95% of such calculated confidence intervals would include the true value of the parameter. Conceptually, this is something very different from what practitioners of Bayesian statistics refer to as the credible interval. Subjectively speaking, the Bayesian credible interval is more intuitive and easier to explain, and is consistent with the Bayesian language of beliefs. But depending on who you listen to, the Bayesian credible interval and the frequentist confidence interval are either very important metrics or not meaningful at all. I'm not here to tell you what to believe. My role here is to explain what the Bayesian credible interval is and where to find it. Whether or not you decide to use it is up to you. In any event, you can gather similar insights just by looking at the plots for the posterior distributions. With that said, let's visualize our chain. So it looks like there are some nice Gaussian distribution shapes for the posterior distributions for our input parameters. But the trace plots don't look as nice as previous trace plots that we've seen in the past. The trace plots here look a little loose, and the mean values seem to bounce up and down a lot. This suggests that our model is okay, but not great. Nevertheless, let's use this model to try to make some predictions. In the past, we've used our Bayesian models to make predictions within our datasets. For example, we would pick new values for x that were within the x value range of our existing datasets. And then Turing would make predictions about the probability distributions, about the dependent y values. For time series analysis, making predictions is all about trying to predict the unobserved future. Now, trying to predict the future is perilous business. But let's give it a go to see what happens. In this section, we're going to use our Bayesian model to try to predict the x values for 10 time steps into the future. We're going to start by setting up a matrix with 12 rows and 1,000 columns. When using the AR2 model, in order to predict 10 steps into the future, we need 2 initial seed values. In this case, we have those values since it's already part of our original dataset. That would be the x values at time 50 and at time 49. Now, we need to use a for loop to fill the rest of this matrix. Each row of this matrix is a time step, and each column will contain the values for those time steps, calculated by using a parameter value randomly sampled from the posterior distributions of the parameters, which are found in the chain variable. You may want to pause the video here to spend some time going through this code. Conceptually, it's the same thing that we did earlier, but we're using the equation for the AR2 model to extrapolate into the future. And we're doing it 1,000 times. Click on the Julia logo icon and click on the table icon for the x_forecast variable. This matrix contains 12 rows and 1,000 columns. Row 1 is time step 49, and row 2 is time step 50. Note that all of the values in row 1 and row 2 are the same for all columns, since these are our initial seed values from the original dataset. Row 3 is time step 51, and row 4 is time step 52, and so on. Row 12 is time step 60. Each column represents an individual forecast, so there are 1,000 forecasts. Now that we have the forecast data, let's visualize it to see what it looks like. For plotting, we just want to plot rows 2 through 12 to capture time steps 50 through 60. The green lines are the 1,000 forecasts. This forecast looks similar to a random walk, but is slightly more informative since our forecast looks back 2 time steps with every step forward. you can see that the further out you go, the less certain the forecast is. Let's add the mean values for these forecasts to our plot, just for reference. Remember, these mean values are just for reference, and not the actual forecast. The forecast is the distribution of all possible forecasts. Now let's talk about this. Is this forecast useful or not? It's definitely better than using linear regression through this entire dataset, and then simply extending the line. And it's better than using a naive random walk, since the random walk is completely random. The Bayesian AR2 model is informed by data from the recent past, so it doesn't rely on the entire history. But it does use a noise factor that's based on historic data, so it's not totally random. But this forecast has a pretty wide distribution, so is it really that useful? If your boss came to you and asked you what the value of X is going to be 10 months from now, and you replied with this forecast, what would be the reaction from your boss? If your boss is looking for a specific value, then this forecast is not very helpful, since the value of X can be anywhere from less than negative 0.5 to greater than positive 0.5. On the other hand, if your boss is monitoring a process that has an upper limit and a lower limit, then this forecast might be useful. If the forecast is within the acceptable limits, then your boss knows that nothing needs to be done. But if a significant portion of the forecast is outside of those limits, then your boss knows that something needs to be done in order to manage that risk. Pretty cool, right? We covered a lot today, so let's pause for a moment and discuss some of the potential issues with time series forecasting. Now, before you go off and try to predict the future, you should know that no one can predict the future. One thing that we know for sure about all forecasts is that all forecasts are wrong. The real question is, how wrong is your forecast? By using a Bayesian approach, you can provide a probability distribution around a range of potential future outcomes. Adding a Bayesian approach to your time series analysis will provide you with another level of insight to help improve your odds of making your forecast a little less wrong. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!